Alright, this is the section for momentum that most people remember, and when you have two moving objects that make contact with each other, they undergo what we call collision. Conservation of momentum is used to analyze all these collisions, so they need to be internal, and Newton's third law is also very useful here. It tells us that the force exerted by body A on body B in a collision should be equal and opposite to the force exerted by body B on body A. During a collision, external forces are ignored, so we don't worry about all those other forces. The time frame of this collision, or any collision, will be very, very short, and the forces are impulsive forces, so they're very high force, very, very short duration when they happen. And you can see a force diagram for the two billiard balls as they knock into each other and kind of what happens to each one. In a collision that's called elastic, we also call these hard collisions. There's no deformation, there's no kinetic energy loss, they basically just bounce off of each other. In an inelastic collision, there is deformation and kinetic energy is lost, so typically you have two things that will collide and they'll stick together. In a perfectly inelastic collision, they actually do just stay together the entire time. The objects stick together and become one object. Deformation does occur, and we do lose some kinetic energy here. Notice that no kinetic energy is lost in elastic, but in the inelastic we do lose some kinetic energy in each one. In the perfectly inelastic collisions, these are the simplest type of collisions. After the collision, there's only one velocity since there's only just one object. Kinetic energy is lost, as we said that, and explosions are basically the reverse of a perfectly inelastic collision in which kinetic energy is gained. And you can kind of see that as we go through some of these example problems. Here's our first example problem. You have an 80-kilogram roller skating grandma. She collides inelastically with a 40-kilogram kid. They want to know what is their velocity right after the collision, and finally how much kinetic energy is lost in this. And those are the two things that they want to know about this problem. So let's go back to the problem again here. And here we've got Granny, who has a mass of 80 and a speed of 6. We have the child of a mass of 40 and a speed of 0. So after the collision, you'll notice that we don't know what her speed is and we don't know what his speed is. We can use the very simple equation, the momentum initial, the sum of the initial momentum, should be equal to the sum of the final momenta. The mass of Granny, we'll put m, and then we'll put g times the speed of Granny, plus the mass of the boy times the speed of the boy, and these would be initial, so we're going to put little i's here, should be equal to the mass of Granny final times the speed of Granny final, plus the mass of the boy final times the velocity of the boy, and that would be final. We know that the velocities of the two should be the same, so we can just basically make this side of the equation mass of Granny plus the mass of the boy should be combined, and then we can just say the velocity of the boy final. In order to complete the problem, what we'll do is let's go ahead and plug everything in. The mass of Granny, we said, was 80 kilograms. We know that her initial speed is 6. We know that the boy is sitting still, so there is no momentum there at all. And then we have the mass of Granny, which is 80, plus the mass of the boy, which is 40, times the final speed. And if you solve for final speed, you end up with 4 meters per second. Because this is not an explosion, we don't really need to call this initial mass of Granny, don't need the initial mass. These masses will not change, so we can just leave those extra things off. The second thing they want us to do is how much kinetic energy is lost. The change in kinetic energy here should be equal to the final minus the initial kinetic energy. The final kinetic energy is 1/2 of 80 plus 40, and we can multiply, so that's 1/2 mv squared times 4 squared, because that was our final speed, minus 1/2 of just Granny times her speed. And at this point we notice that we've lost 480 joules of kinetic energy. And that is the end of the Granny problem.